Welcome back, everybody. I'd like to move on with our series. We just talked about marine sediments and the different types of environments in or near the ocean that can create and even transport sediment. So now I want to talk about the sediment itself, and how understanding that sediment and the characteristics of it can help us understand past environments. So let's talk about how sediment forms in general. It typically breaks down into two types of weathering: physical and chemical. For physical weathering, we're going to look at four different features here that can potentially break up the rocks. So near surface fracturing is where a lot of processes on the surface can break rock into smaller pieces. These can be rocks pulling away from a steep cliff. In the image you see, just the weight of gravity on a steep cliff can kind of pull the rocks away. Also, if you have rocks that are just lifted up to the surface, they're experiencing less pressure just by being not buried underneath a bunch of rock. So they start to expand just from that release of pressure, and that fraction can break off pieces of rock. Something we see actually really quite a bit here in California is frost and mineral wedging. I've described this to some of you, but this is one of the reasons we see a lot of rock falls in Yosemite. This is because during the winter, when it rains and then when it snows, the liquid water gets into any cracks that exist in the rock, and water expands when it freezes. So it actually breaks the rocks even more. And as that water transports down into these cracks, it can also leave behind minerals like sodium chloride, and those also grow into those fractures and they can break the rocks apart. So frost and mineral wedging is actually a very big erosional agent. The thermal expansion is a little less important. It's typically we see more thermal expansion during wildfires, but a little bit of fracturing can happen just as a result of the day heating up. But it's really, scientists are still kind of debating whether or not this one's even particularly important, since it's not nearly as dominant as frost and mineral wedging, or this next one, which is biological activity. This is when tree roots actually grow down into the rocks, and as the roots take hold and then expand, they act a little bit like that expanding water, and they crack open the rocks there. And on top of that, you also have burrowing animals that can sort of bring material up from down in their burrows to the surface, and that exposes that sediment up to the surface. And the act of creating those burrows is an erosional agent. They can break it down, break the rocks down into sediment. Okay, so chemical weathering is when you have, like it sounds, chemical processes. So the first one I want to talk about is dissolution. This is where some minerals are soluble in water. They stay dissolved in water. And most like waters in nature are sort of weakly acidic. And so those minerals and things in the water can react with minerals in the rocks and sediment and soil. And anything that the water kind of can dissolve will get picked up in the water. So if the water runs over rock and any of those minerals trapped within that rock are soluble, that water will kind of dissolve them in and transport them away. And they can be, that material can also be good for plants kind of down the line. So if you've got water flowing through a particular area of rock and it picks up a lot of nutrients, that can actually carry those nutrients away into the soil. Oxidation is one you might see quite a bit. Some minerals, anything that really contains iron, when it's exposed to the Earth's atmosphere, either water or the oxygen in the atmosphere, they can form oxide minerals, which is what causes that characteristic red or yellowish color you see. So that's essentially chemically changing the rock into other rock. Hydrolysis is an interesting one. This is when you get silicate minerals. So I think we've talked a little bit about silica and silicate. It's that lovely SiO4 tetrahedron we talk about a lot. Any silicate minerals, when they're exposed to water, especially if it's a little acidic, they react with that water or that acid, and that takes the original materials and it converts them into other materials. So this is a long way of saying you get water reacting with silicates in the ground, and that actually creates what we know of as clay. And that stuff's really carried away. So hydrolysis is like the main formational agent of clay-rich soils, because you've got lots of these silicates in there. We'll talk about that in a minute. The last one is biological reactions, and this is where decaying plants actually, this is actually a interesting plant too. When they're dying, they send off these biological signals that create acid, and that can actually break down rocks, and they produce some bacteria that can also break down rocks. And so these are biological reactions are not nearly as prevalent as your other three, but they're still interesting to kind of note because they can play into the way that sediment is created and carried away. So one thing that comes up when you look at this is all very cool. I'm sure all of you find it incredibly cool. But why are there so many different products of weathering? Like weathering creates so many different kinds of sediments. Um, it depends on there's so many varieties of rocks that are being acted on by erosion and weathering, and there are so many different types of erosion that we see that just tends to just create a really large range of minerals. And predicting, what's going to form, it depends on things like the climate and it depends on the material being eroded. So, for instance, this is a really cool. What is this? This is a limestone. Sorry. Um, so limestones have a lot of minerals within them that are soluble in water or acid. And so this is what I was talking about earlier with that dissolution. This is where water or sort of slightly acidic water will run over the surface of the limestone and it will dissolve um, the soluble minerals into the water and it'll leave behind these little gaps in the rock that used to have the minerals in them. Other rocks, like anything rich with quartz, is pretty resistant to this specific type of erosion because anything rich with quartz doesn't typically, like quartz itself doesn't typically react with water or slightly acidic water. Um, this is actually looking at rocks that are made up of lots and lots of different types of minerals. So pretty much all sediments and soils and rocks contain more than one mineral, and every mineral within there is going to react differently to weathering. So feldspar, these little pink and cream colored crystals you see in here, these guys chemically weather to clay minerals. So if they undergo any kind of chemical reactions, they'll typically form clay. But if they undergo physical weathering, they'll probably form sand. And this is because the chemical reactions actually change the types of minerals into other things, whereas the physical weathering doesn't really change the chemical makeup. It just picks out the quartz that's particularly susceptible to that kind of physical erosion. So the chemical process makes your clay, and the physical process makes your quartz, but it's the same root material that's being eroded. Typically, if you have like dark mafic minerals, those will usually chemically weather into clay or iron oxides. And literally anything quartz is going to physically weather. Quartz is going to physically weather into sand because it's just got that texture already. So if you look at the photograph, something that's just showing here is that the mineral composition, the grain size, the texture, basically what you have to work with is going to affect what kind of sediments you get out of the erosion. And I want to kind of not play up, but just emphasize the importance of fracturing already being there. Because if you look at this image, there's tons of fractures in this image. Fractures sort of are like this positive feedback mechanism where the more fractures you have, the more surface area is exposed for weathering. And the more gets weathered, which exposes more surface area, which causes more weathering. So fractures lead to fractures lead to fractures. And so usually if you have an area with lots of rocks that are susceptible to fracturing, they're usually lower in elevation because they've just been eroded away, or they'll form really steep notches in these ridges and hills. So if you see an area that's really old and covered in fractures, it's probably been heavily, heavily eroded because those fractures are dead giveaways that erosion's happening. Let's get into like everything I've described so far is creating little bits of rock. So these are known as clasts. Okay, so clastic sediment is sediment that's made up of loose fragments of rocks and minerals. So when it turns into sedimentary rock, the actual rock you're dealing with depends on, of course, the sediment you had involved. So this is usually broken down by size. So this is a table kind of organizing the size range for the particles, the name of the sediment, and then the particle name within that sediment. So if you've got a sediment that's classified as a gravel, it's got larger particles that are somewhere between 2 and 256 millimeters. And so the actual detailed breakdowns, if you've got something that's larger than 256 millimeters, then it's a boulder. Slightly lower than that's a cobble, slightly lower than that's a pebble. So in the image I just clicked up, the rock with the Sharpie on it is a cobble, and the rocks around it are pebbles and varying into granules. Now granule and sand, those will kind of smear together. It's kind of hard to tell. Gravel's usually these really big particles, whereas your sand is it's got a range to it. Sand can be either uh, fine grained, like this really, really fine grained sand. It can be medium grained, or it can be pretty coarse, depending on the essentially the agent that carried all the sand to the area. Like if it was really strong wind, it might have been able to pick up slightly heavier sand grains, or if it was a particularly weak wind, it might have only picked up your really, really fine grained sand. And if you get into the really, really tiny particles, then you're talking about something that we just generally call mud. And that's when you've got something like silt or clay. This is a little bit of a look at, these are mud cracks, and this is actually a mixture of silt and clay. Silt and clay are really similar in size, but you can always tell the difference because clay is going to feel kind of soft in your hands, like slippery, and silt will feel pretty gritty. So silt is made from quartz. Silt is that physically weathered feldspar I talked about, whereas clay is that chemically weathered feldspar that changes it into something else. So silt is kind of retaining that granular feel from the original rock, whereas clay is just chemically changed. And you're going to find silts and clays in sort of these stiller waters like lakes or really, really sluggish streams because they're finer particles, right? Remember, things that don't have very much energy will not carry particularly large particles. So what else can we learn? What else do we want to know? There's just a big relationship here that I kind of want to tie together for you, that the size, the shape, and the sorting of your class is going to tell you a lot about what happened to them. So let's talk about the shape. We actually covered shape a little bit. Angular clasts are ones that have sharp edges. Kind of makes sense, right? A lot of them will have sort of a mixture of like angular and a little bit rounded. We consider these to be sort of in the process of rounding. And then you can have these fully rounded clasts, and they have really smooth curved surfaces. And we typically can conclude some things about how they were formed, and maybe even how far away from their source they are. So as the material moves farther and farther from the source area, as the sediment gets transported, it's going to get rounded more because it's just had more time to bump into other sediment and get shake it up. So if you take a big bag of angular rocks and you shake them for an hour, you're going to start breaking them down into rounder particles. Steeper slopes are going to contain your angular sediments, like those mountain regions we talked about. But if you've got like stronger rivers and ocean waves, those can lead to more rounded shapes. They can carry things a little farther. Whereas your glaciers, your landslides, maybe even fractures within the mountain, those are going to give you those angular shapes. So the shape can not only tell you about the specific agent of erosion, but also how long it's been eroding. The longer it's been eroding and the farther away it is from the source, the more round it's going to be. All right, and then sorting. Sorting is kind of cool. We talked a little bit about sorting. This is kind of like that graded bedding I was talking about, like at river deltas or even oceanic deltas. So your steeper slopes are going to contain sediment that's not particularly well sorted. So sorting just refers to like the size range of clasts in a rock. So if you've got a wide range of sizes, like cobbles and pebbles and maybe some clay, then it's considered to be poorly sorted. And if you've got something that's got a decent mixture, like maybe you're getting into similarly sized particles, but maybe you've got some sand and then maybe up into some cobbles, you're dealing with medium sorting. And then if you've got well sorted sediment, that's a class that pretty much all fall into that same size range. And these tell you about the agents that transported them, because steep slopes are areas where you have like less consistent erosional agents like glaciers. That's going to have sediment that's pretty poorly sorted and usually angular, because it's not a gentle or steady process. Stronger turbulent rivers, ocean waves, those can carry lots of different size ranges, but if you've got less turbulent currents, then you're kind of starting to limit your size range. So the speed, the energy your moving erosional agent is carrying, that's going to determine the sorting. Like, remember we talked about really fast moving rivers can carry a huge range of sizes. Now as they get slower and slower, they have to start carrying only smaller and smaller sizes. And when you get all the way into stuff like sand and clay, that stuff's really only going to be transported by wind. So glaciers can move any size range of particles, whereas wind can really only move the fine grained particles. So remember, the actual agent of the erosion and sort of the energy that's associated with it, that can have a huge impact on the sorting. And the last one to talk about is essentially distance, but I kind of touched on that before. So let's take a look just to kind of highlight this point here. As on the left side of this image are rocks that are just starting to erode, and they're being carried away as time goes on. And so the farther from the source means they get smaller and they get rounder, and they get exposed to more and more types of erosion as you go along. So the steepness of the slope can affect the how much erosion is going on and what's going to happen to the particles. Remember, the steeper the slope, they're going to be angular. You can kind of have a range of particle sizes. The strength of the current, and we mean like water current, wind current, the speed of the glacier is even a type of current. The strength of that current, the stronger it is, the more range of sizes it can carry. So you're looking at, actually, with strong currents, you're looking at particularly poor sorting. And the agent of transport itself can impact like what kind of sediment gets deposited. So remember, go back to the very top source here. We're trying to figure out like how does this affect what kind of sedimentary rocks form? And we're going to get into the specific types of clastic sedimentary rocks in the next video. But I want you to keep in mind that there are some really important factors that are going to determine what sediment ends up where, and that sediment is going to turn into the sedimentary rock. So if you've only got really well sorted sand grains from, say, a wind agent, then you're probably going to get sandstone. Whereas if you've got like really turbulent current that deposits lots of differently sized particles, maybe you have something that we typically call a conglomerate or a breccia. So I want you to keep in mind, like, the big picture from this video is that the type of erosion, the distance a particle's traveled, the agent that's actually doing the traveling or the carrying, those are all going to tie into what kind of sediment forms where. And then the next sort of part of that puzzle is, okay, that's going to turn into a sedimentary rock. So that's it for now, and I will check in with everybody later in the week. We're going to be working primarily on our curriculum projects this week, so most of your sedimentary rocks learning is going to be through these videos. So check back in. All right, everybody, have a good night.